Assalamualaikum warahmatullahi wabarakatuh, and a very good day albeit to the internal examiner as well as my supervisor, Sir Muhammad Nur Amin bin Zakaria. My name is Muhammad Umar Hakim bin Muhabbal with ID number 25534, final year student of PETROLEUM Geoscience in Universiti Teknologi PETRONAS UTP. For this presentation is about my final year project FYP, which titled as an investigation of possible impact crater at Langkawi using gravity geophysical method. For this presentation, we will be divided into 5 topics, which start with introduction, and then literature review about the general geology in the study area, as well as the geophysical method that will be used, and then methodology on how we will going to acquire the data, and then results which will be processed and output by several softwares, and lastly ended with the conclusion part. In the first topic, introduction, it will be consist of the problem statement of the project, the objective that need to be achieved, and will be discussed about the study area of the project. Tija 2000 and Siti Aisyah 2001 has reported that there is a near circular feature at Hulu Melaka, located at southwest of Langkawi by the aerial photograph. This irregular oval hill topography enclosing the area of Masuri Tomb is suspected to be the remnant of the impact crater, which named as Masuri Ring. In Malaysia, there are two famous impact crater events, which located first at Bukit Bunuh, Lenggong, Perak, and the second one is at Hulu Melaka, Langkawi, Kedah. Compared to the Bukit Bunuh impact crater, this Masuri Ring at Langkawi is less studied due to the lack of evidence, of physical evidence, such as presence of surat resha. Surat resha is a rock that undergoes shock metamorphism, or we can call it as a high temperature, low pressure process, which only can happen due to impact crater event. The impact of the crater changes the properties and characteristics of the impacted soil and target rocks at the point of impact and surrounding area. Thus, the changes of the area can be used to determine and derive the structural information by using the geophysics and drilling data, which stated by the Pilkington and Grieve in 1992. Hence, this project is mainly to investigate the presence of possible Masuri impact crater at Langkawi by using geophysical gravity method. And then we're going to interpret the gravity anomaly maps qualitatively and quantitatively to prove the presence of Masuri impact crater. The study area will be located at the south central of Langkawi Island, in between of Kampung Ulu Melaka and Masuri Tomb near at Kampung Mawat. As you can see on the maps on the left side, the red circle is marked as the Masuri Ring 1 and the yellow one will be marked as the Masuri Ring 2. Both of these Masuri Ring is coordinate as 6 degree 21 north, 99 degree 47 east, and 6 degree 20 north and 99 degree 46 east. The study area will located 14 km westward from the main city of Langkawi, which named as Kuah Town, 300 km northward from capital city of Perak, Ipoh, and 520 km from Kuala Lumpur, capital city of Malaysia. The study area is quite flat as the area is covered with paddy field, which will be easier to do the gravity geophysical data. In this second chapter, literature review, we will discuss about the general geology at Langkawi Island, as well as the impact crater in details about the morphology, the types, and also the process that will undergo to form the impact crater itself. According to Jones 1978, Langkawi Island have a various formations, which are the Machincang Formation, Circle Formation, Singa Formation, Chopin Formation, as well as the Gunung Raya Intrusion. According to Tija Amazon 2002, the host rock of the impact crater is belong to the Singa Formation, which make this Singa Formation as our interest bed of geology. Machincang Formation is the oldest clastic rock that have been identified in Langkawi, which aged in Cambrian to Ordovician. Its lithology are the sandstone, mudstone, conglomerate, and siltstone, and these were deposited at wave-dominated delta. Going younger, the Circle Formation is aged in Ordovician until Middle Devonian. It is one of the carbonate sedimentary rock which the lithology has a darker color of limestone and deposited at shallow and deep ring. Going upwards, the Singa Formation is aged in late Devonian to early Permian. It's another clastic sedimentary rock that can be observed in Langkawi, and its lithology were only mudstone and siltstone. It were deposited at continental slope and continental shelf. Chuping Formation is aged at early Permian to late Triassic and is another carbonate sedimentary rock in which have the brighter color compared to the Circle Formation and deposited at shallow marine. Lastly, Gunung Raya Intrusion. This rock were aged in Triassic to Cretaceous and classified as one of the Inu's only rock at the Langkawi Island, which make the Langkawi Island to be uplifted. Those 5 formations were deposited scattered around the Langkawi Island, as you can see in the map on the left side. This is a geological map of Langkawi by Lee Chai Peng in 2014. The geological history of Langkawi were also being done by Lee Chai Peng also in 2014, as you can see on the figure on the right side. Enough explanation about the general geology in Langkawi. We will now explain in details about our subject matter in this project, which is the impact crater. Impact crater have been explained as a circular to nearly circular shape or bowl-shaped depression cavity into the earth by the Pilkington et al. 2001. This is due to the impact of meteorite that hit the continental surface. National Aeronautics and Space Administration (NASA) has explained the meteorite as a meteoroid, small size of comets or asteroids that survive a trip through the Earth's atmosphere and hits the ground. The impact crater, according to Jimin et al. In 2017, it will change the properties and the characteristic of the impacted rocks and the surrounding area. There are several distinctive marks that can be used to determine the presence of the impact crater, which are Sylvite breccia, shatter cones, macroscopic features such as planary formation features by Tija and Mazenat in 2017. Scott et al. Grown that tectonism, erosion, and burial will make the impact crater either destroyed, obscured, submerged, or difficult to be seen with the naked eyes. Crater structure has 6 morphology features that can be seen. The first one is floor. Floor is the flat surface at the bottom of crater. Second, walls. Walls is the interior side of the impact crater and sometimes it can be quite steep. Next, rim. Rim is the top edge of the surrounding ground where the ground material will be pushed away during the impact. Central peak is only can be seen at the center of the floor and only can happen from complex times of crater. The development of this central peak is due to the ground materials that will be pushed back after forming the rim structure. Injecta is the materials that fly upward and upwards during the impact and settle down around the surrounding area. Injecta will be thickest around the crater and thinnest further away from the crater. Lastly, rays. Rays is a bright streak that extend away from the crater. Next, let's talk about the types of impact crater. Impact crater structure can be divided into 2 types, which are simple and complex type. Simple type is caused by a small meteorite and usually less than 5 km in diameter. Simple type doesn't have a central peak features, as you can see in the figure on the left downside below, and only undergoes 2 processes of the impact crater. Compared to complex type, it is caused by bigger meteorite and usually more than 3 km in diameter. It has central peak features, as you can see on the right downside, and undergoes all 3 processes of impact crater. There are three process stages in forming the impact crater structure. It starts with the contact and compression stage, next excavation, and lastly the bonification and collapse stage. The contact and compression stage starts when the meteorite itself hits or touches the surface ground. The impactor will decelerate and compress the surrounding area and produce the destructive shock wave and induce the shock metamorphism around the rocks by according to the Melosh in 1989. According to Melosh in 1989 also, this contact and compression stage is only took a few tenths of a second. Next, the excavation stage. Excavation stage is when the impacted material were melted, vaporized, or either injected outwards. According to French 1989, the impacted materials will accelerate away from the contact points of impact. The rim will be developed topographically upwards as the material were uh, away from the contact of point, according to the Maxwell 1977, Griff et al. 1977, Griff and Sintala 1981, and Melosh 1989. There is only a small volume of the impacted material we preserve and undamaged. Lastly, the modification and collapse stage. This stage is only happen when the transient cavity from the excavation stage is not stable and falls under the gravitational force according to French 1989. It is because or only the gravitational force and not because of the elastic rebound properties. It involves of uplift of the central region and inwards of the collapse of the rim, which will be produced and forming the central uplift. The rocks at the bottom will resist and to compress and deform and eventually snap back and push up the central peak according to 1989. As you can see on the figure on the left side by French 1998, this explains about the simple and complex impact craters formation stage. On the left side is the simple type. As you can see, the final crater will does not have the central uplift features, and the right side is the complex impact crater, and the final crater will form the central uplift features. In this third chapter, methodology, we will discuss about the flowchart work and also the software that we're going to be used to produce an output and outcomes of this project. This project starts with the pre-data processing phase where we did the literature review and desktop study about the general geology of Langkawi as well as the subject matter itself, impact matter. Then we move into the data selection and validation phase where we select the satellite gravity data by EGM, Earth Gravitational Model 2008, as well as the ground gravity survey data that were acquired in 2014 by one of the UTP students by using the SkinTrack CG5 gravimeter. And then the data will be undergo some correction and reduction to produce the final Google gravity anomaly data. This final Google gravity anomaly data will then be used in Oasis montage software to produce the Google gravity anomaly map. The final Google gravity anomaly data also will be applied frequency filter, either high pass or low pass, to produce residual anomaly map and original anomaly map respectively. All these maps and the data will be used to produce 3D surface and 2D modeling to image or portray the structure itself. And then lastly, all the findings, outcomes, and outputs will be used to write the report. Survey in 2014 used SkinTrack CG5 gravimeter. This gravity survey has a total of 122 gravity stations with a spacing of 100 meter to 300 meter between each of them. The study area also were approximately 4.5 kilometers square. For stations elevation and stations coordinate, it is measured by wireless and Tierney altimeters and global positioning system GPS respectively. The raw gravity data will be then processed by doing some reductions and corrections to obtain the final Google gravity anomaly data. The final Google gravity anomaly data will then used by several software to produce gravity anomaly maps, 2D modeling, and 3D surface. As you can see on the left side of the slides, it is the gravity station of 2014 acquisition gravity survey in between Kampung Ulu Melaka and Kampung Mawar. These are the several softwares that will be used in order to produce outputs and outcomes of this project. The first one, GeoSoft Oasis Montage, is used to produce gravity anomaly maps, which are the Google anomaly map, regional anomaly map, and residual anomaly map. Next, Golden Software Surfer will be used to produce the 3D surface. And lastly, S3ArcGIS and Global Mapper software will be used to produce other several maps. Next, we'll be discuss about the results. In this topic, all the anomaly maps, 2D model and 3D surface will be shown and will be interpreted qualitatively and quantitatively. The first result is the BGI satellite Google map. This Google map has a maximum gravity anomaly value of 22.78 milligal and 0.11 milligal as the minimum gravity anomaly value. The high gravity anomaly, which can be seen as a hot color, is obvious at north and west part, while the low gravity anomaly value, shown as the cold color, is dominated at the center. This Google map is very regional as it measures the whole Langkawi Island gravity contrast. We require a more close-up map to study the impact crater event. As you can see on the left side, this is the satellite Google map. The red circle is marked as it's suspected to be the remnant of the impact crater. As you can see on the map, the surrounding of the red circle has a similar gravity contrast, which makes it harder to interpret or prove the remnant of impact crater structure. The BGI satellite Google map then will be overlaid with the regional geology map, as you can see in the slides, where all the formations that been discovered around the island will be marked according to the number. The first one, 1 Macincang, 2 Sentul, 3 Singa, 4 Chuping, 5 Gunung Raya Ines, and 6 the Alluvium. As you can see on the red circle, where is suspected to be the remnant of impact crater, the host bed for this impact crater structure is Singa Formation. From the Gravity Acquisition Survey in 2014 data, the final Google data will be used to produce this anomaly map. Google Gravity Anomaly Maps usually used by professionals to indicate the horizontal changes in Earth gravitational model. It comprises of both regional field and the residual field. In other words, it shows the average gravity contrast for shallow and deeper part of the study area. This Google anomaly map has a maximum gravity anomaly value of 3.9 milligal and negative 8.2 milligal as the minimum gravity value. The high gravity anomaly, which indicates in the hot color, is dominated on the east side, while the low gravity anomaly value, shows in the cold color, is observed to be dominated at the west side. Circular contrast at the center, as you can see, is suggested to be the remnant of the impact crater. Other than Borer anomaly map, regional anomaly map also will be produced by applying a low pass frequency filter. This left side regional anomaly map is being produced by after applying an effective cutoff of 1000 meter. This only allows low frequency signal or deeper depth anomalies to pass through. This regional anomaly map also has a maximum gravity anomaly value of 4 milligal and negative 7.5 milligal as their minimum gravity anomaly value. The gravity contrast trends can be observed increasingly gradually towards the east side. This is might due to the Gunung Raya Ines rock which deposited on the east side of the study area. As you can see also on the map, there is no circular gravity contrast, which uh, might be because the meteorite does not hit any deeper or older bodies than the Singa Formation. Lastly, residual anomaly map also will be produced after applying a high pass frequency filter. This residual anomaly map on the left side is being applying an effective cutoff of 300 meters, which only allows high frequency signal or shallow depth anomalies to pass through. This residual anomaly map has a maximum gravity anomaly of 0.6 milligal and negative 0.5 milligal as their minimum gravity anomaly value. The high and low gravity anomalies were observed scattered around the study area. The suspected remnant of the impact crater event, which at the center has a nearly minimum gravity anomaly value, which negative 0.5 milligal. Rather than using only anomaly maps to study the possible impact crater at Langkawi, 2D modeling also will be constructed in this work to image the impact crater structure in terms of type, diameter, and depth. There are two 2D model profiles will be constructed in this modeling, which in north-south direction and west-east direction. This 2D model used the Google Gravity Anomaly data as a reference with other four density parameters: alluvium with 1.6 gm per cc, colluvium 1.78 gm per cc, metasedimentary 2.3 gm per cc, and as well as the bedrock signal formation in 2.67 gm per cc. The structure will be discussed is in the north and south direction. The impact crater structure can be shown clearly and be classified as a simple type impact crater with no presence of central peak morphology. This model also indicates that the impact crater has a 2.5 km in depth and 700 in diameter. The other 2D model structure is in the west-east direction. This 2D model also gives a good agreement with the first model in the north-south direction, as the impact crater shown in these two models were classified as a simple type impact crater with no presence of central peak morphology. This 2D model also indicates the impact crater has a 2.5 km depth and 700 meter diameter. Surface also were being constructed in this work by using the golden software surface. This 3D surface were mainly to evaluate the possible impact crater is either in influence of surface elevation or not, based on the 3D surface on the left side, which use the gravity anomaly data. It shows the depression cavity which marked by the white circle. On the right side, the 3D surface were constructed based on the elevation surface, where we can see the surface that marked by the white circle is quite flat. Hence, it's proven that the presence of the Masuri ring impact crater. Last topic for this presentation will be the conclusion part, where we will be discuss about the conclusion, either the presence of impact crater can be proven or not, and some recommendations to improve this work. By using all sorts of findings, outcome, and outputs, the presence of Masuri ring impact crater can be proven, with classified as a simple type with no central peak morphology. This Masuri ring impact crater also has a 2.5 km in depth and 700 meter in diameter. This works also prove that the integration between the geophysics and geology helps in determining the remnant of impact crater structure. Below are some of the recommendations that can be used to improve these works. The first one, magnetic survey. Magnetic survey also usually used in industry to delineate rocks boundaries. Other than that, borehole drilling. This is very favorable as it can give out the physical evidence such as the Soviet Russia, where Bukit Bunda impact crater were proven with the presence of Soviet Russia rocks. Next, acquire recent data. I would love to go to the Langkawi itself to do the new magnetic and gravity survey. Lastly, study other Masuri ring as reported by Tija that Masuri ring were reported as two circular features where the other ring were located at the northwest part of the Masuri ring one. Last but not least, I would like to express my gratitude to University Technologi Petronas UTP institution as well as Sir Muhammad Nur Amin bin Zakaria for his hard work, guidance and supervision in my FYP. Not forget to mention to the internal examiner as well as the external examiner for lending their ears and spending their time to evaluating my final year project. Thank you.